Welcome, and it's good to be with you. I'm going to walk you through section 9.1 today. Yes, we're going to go over 9.1, part 1, which will be day 1 for us. And just looking at sequences, I doubt there's anything earth-shattering that you're going to hear today because this is a little bit of review of material that you've had in previous courses. So it really shouldn't be too hard. But people do get confused by sequences, so that's why I want to take the time to just kind of go over the highlights, and then set you free to work on WebAssign. I'm sorry, my math lab on the assignment that will be there for you. Before we get started, we need a little riddle. What do snowmen eat for breakfast? Anybody guessing this? Frosted Flakes. All right, here we go, guys. Let's look at defining a sequence and then what are the layouts for arithmetic and geometric sequences. So I'm going to, well, you know what? That wouldn't be bad. Just a quick review on some of the AB material, the limit work. First thing I notice on this limit is that it's going to infinity. And when it's going to infinity, we're looking at the degree comparison for the degree on top to the highest degree on the bottom. And you know, immediately the squareds are popping out at us as the highest degree top and bottom. When that is the case that they are the same degree, we know the story goes that really this becomes a ratio of 2 to 4 or 1/2. You know, we could honestly say that these two functions are growing at the same rate if you think about the information on section 9.3, because we do come out with an actual limit, and so there you go. The next one is a good review from AB, where we had a special sine function that we worked with. It was the limit as x goes to 0 of sine of something, and it didn't really matter what that something was, just the fact that it was the same argument of sine over a polynomial, or a polynomial on the bottom. So in this case, we notice that we've got 4x compared to x, and obviously not the same, huh? So the trick is, well, let's make this the same. So I'd love to see a 4 in there. It's going to have the 4x, but in order to do that, I need to multiply really by 4 over 4, don't I? So what I'll do is I'll break this up, and we'll have the 4 on the bottom and then this 4 out in front of the sign, multiplying by the sine of 4x. And the story goes, let's just swing. We can move our 4 out front. I'll get rid of that parenthesis. And I still have 4 over 4 essentially, but I'm going to calculate the limit first, and then I'll multiply by that final 4. We know that this limit goes to 1, so here, even though it's 4x over 4x, that will go to 1, and I pick up 4 times 1, so answer's 4. You knew it all along, didn't you? All right, defining a sequence. A sequence simply is a list of things that are generated by some rule. So there is some orderliness to it. More formally, a sequence is a function whose domain is the set of natural numbers, such that the range of the function are called the terms of the sequence. So really, this list out of all the terms, this is the range of your function. It's the output. The input is just really the number that we're putting in for n. So n, which is a member of the natural numbers, so like the natural counting numbers, 1, 2, 3, 4, 5. So those natural numbers, that is our domain. And so we put in those, and we come out with different terms of a sequence. If the domain is finite, then the sequence is a finite sequence. And if the domain is infinite, then the sequence is an infinite sequence. You could guess that, couldn't you? Meaning that the terms never stop, that pattern of terms will continue. A sub n is called the nth term of the sequence. Sequences can be expressed by, just an ample listing of the number of terms. We'd separate them by commas. You may be familiar with some things where we add values together. That is referred to as a series. A sequence, oh, I should have done something different here. A sequence is really just an enumeration, a listing of the members of it, and maybe you recognize this one as the Fibonacci sequence. 1, 1, 2, 3, where you were adding the two previous terms to get the next one, and 2 and 3 make 5. Yep. The other way is we can write an explicit function defined by some rule for the sequence. So, like 2n is my rule. So a sub n is 2 times n. So if I have my a sub first term, well, I'd put 1 in and I get 2 out, right? My a sub second term, I put in 2 this time and I get 4. And obviously I've made a pattern of the even numbers, haven't I? And so on. The rule of the sequence set off in braces. Oh yeah, sometimes the rule of sequence can be expressed just in braces like that, rather than writing out an explicit rule of a sub n. A sequence is a function f whose domain is a set of positive integers. We talked about that. Sequence notation. Here's that one way we can write the rule using braces and just put the rule in there. And there's an example of 3 to the n, so powers of 3. We can actually graph this stuff out too. Here you see the horizontal axis containing the values of n, the domain of the function, and then the outputs are coming into the height of the a sub 1, the a sub second term, third term, so forth. So they have a little example here, lists the first 4 terms and the 10th term of each sequence. So let's just practice. A sub n, if we want to write the rule of sequence, would be 5 plus 10 to the nth power. My first term, I would put 1 in, which would be 5 plus 10 to the first, or 15. My next one, I'd put a 2. Let me do something just a bit different because that disappearing ink might be handy here. Put in the 2, and oh, I have no smart ink bubbles. Alrighty. So I have 15. That's going to disappear. Things are not working well here, guys. Okay, I'll put in 2. For n, that would be 100 plus 5, so 105. Put in 3, so it's power of 3. That'd be 1,000. 1,000 plus 5. Put in 4, I'm going to have 10,005. And that would be the first 4 terms, correct? The 10th term would be 10 to the 10th, so we have 10 zeros plus the 5 at the end. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it would be a plus 5. So there's the 5 at the end, taking the place of that 10th zero. So what are we up to, like billions? Yeah, 10 billion. Hopefully I'm right on that because I'm not counting them out again. This one's an interesting one. We're going to have, this will be actually an alternator. It's going to alternate positive and negative. And we will have to decide, it actually might be negative followed by positive once we get into this. And that rule, well, we could write a sub n is equal to -1 to the n plus 1, n squared over 3n minus 1. Would be our rule of sequence. And then we'll just start with a sub 1. So let n be 1. And it actually is going to start positive then if this was an n plus 1. So we put 1 in here and I have -1 really to the second. So that's why I said it's going to start as a positive. Put 1 in and square it. I'm going to have 1 over 3 minus 1. So it looks like 1/2 is our first term. Then we go to 2, so I'm going to have -1 to the third. 2 squared is 4, and then 3 times 2 is 6. 6 minus 1 would result in a 5. So 4/5 odd power with a negative is going to be negative. And so on. You could keep playing that out. I'm going to just keep moving through. That ends up being 9/8 and -16/11. The a sub 10th term actually turns out to be a negative, and it's 100 over 29. And then we've got this other one. The rule of sequence is written just as 6. So what would be my a sub first term? Well, I put 1 in, but I have nothing to put 1 into. So it is simply just 6. This is just 6, 6, 6, 6, 6. And then the a sub 10th term, guess what? 6 again. So just quick do-over on those. On the back page, it says, what do I got there? Oh, I guess this is at the bottom of the first page. I was going on to the second page. A sequence is defined recursively. You have a blank there. When each term following the first term of the sequence is defined with the previous term of the sequence. So these are known as recursive. I think of them kind of as curving back and using the previous answer usually, or maybe the first 2 previous answers. This here is our starter value. It's showing up as our a sub first term. And then you'll notice that this is written kind of interestingly. A sub n minus 1, and this is the a sub nth term. So if I think about, ordering stuff, if n would be larger than n minus 1, correct? And it would be larger by 1 unit. So if this is my a sub first term and this is my a sub second term, you can see how this would be a sub 2 minus 1, which gets us back to the a sub first term, comma a sub 2 term, where n is 2. So that's the recursive. You'll always be able to pick it out pretty easily because you're going to have something that is 1 unit difference perhaps than the resulting term of sequence. Alrighty, so let's get this started. We know our starting value for a sub 1 is 5. And let's see, where was the rule? I gotta write you a rule down. A sub n plus 1, oh, this one's written kind of interesting, is 2 times a sub n. Now, is this a recursive? And this is where n is greater than or equal to 1. Is this a recursive? Well, yeah, it actually is, because here's the nth term, and this is an n plus 1 term. So the term on the left is 1 unit or 1 term larger than the a sub n term. And our starter term is a sub 5, so the a sub second term is going to equal 2 times a sub 1. And that would be, my a sub second term would be 2 times 5, which gives us 10, right? And then I come down, my a sub third term will be based on the a sub nth term, and my n, let's see. Oh, you know what? Here, I'm sorry. This was written a little bit different. I didn't even pick that up, you guys. Scratch that. Go back and erase. A sub n. Just writing it a little different, the results are going to be the same though. So we still have the term that comes prior to this term. And we'll say the a sub third term is 2 times a sub, I'm on my third, so 3 is my n minus 1, which would be the a sub second term, wouldn't it? So a sub 3 is equal to 2 times the a sub second term, which is 10, and that turns out to be 20. And then my a sub fourth term is going to be 2 times the a sub 4 minus 1, which is the a sub third term. So a sub 4 is equal to 2 times the 20 value from before, getting us 40. And the a sub n term would be 2 times a sub n minus 1. Okay. Sequences in which pairs of successive terms have a common. Okay, we are going to define 2 different types of common sequences, well-known sequences. The the arithmetic sequences contrasted with the geometric sequence. The arithmetic, you probably remember this fact, has a common difference. Either we're adding or subtracting a value. And geometric, they have a common ratio. So either we're multiplying or dividing by some common number. And you can kind of see the layout here. We have our a sub first term. The next term is going to take and add a common difference. And then notice how this is always starting with the beginning value, but I'm adding 2 common differences, 3 common differences, n sub minus 1, n minus 1 common differences to the starter value of a. And that will build up a nice arithmetic sequence. This is often recognized as the kind of generic equation for finding the arithmetic sequence term. And it's starting at 2, so that when I go 2 minus 1, I get the a sub first term, and that will give me the a sub second term there, right? Now, what sometimes happens is that we don't always start with the a sub first term, correct? Sometimes they play around with this and give us the a sub fifth term and a sub 12th term, and then what do? You know, trying to find some of those can be a little tricky. I like to kind of remember this formula as well, that no matter what I start with, maybe I'm starting with my a sub n, m, I can find any finishing value a sub n by just remembering that it's going to be the amount of differences that lie between the nth term and the mth term. That's kind of hard to say. And then I'd multiply by that common differences. And it would be like, you know, jumping me to say, you know what, you got 3 common differences between the 4th term here and the 1st term. Well, maybe I have the 15th term and the 12th term. Well, there'd be 15, that was kind of weird, wasn't it? 15 over here, 12 there. So I'd have 15 minus 12, or 3 common differences to add to the a sub 12th term to get me to the a sub 15th term. All right, geometric sequences, well, that's all about multiplying and going from one function to the other, like the 2n1, right? And then it would be 2, 4, 8, because I'm just multiplying by 10 each time, which I'm struggling, 16, 32, and so on. So each time we're multiplying by a common r. You'll notice here they continue to use the beginning value of a and just multiplying by more r's times the beginning term to get each of those terms. This is a nice way to think of your general nth term of your geometric sequence. Often you'll often say, well, the nth of a sub n term starting at a sub 1 times r to the n minus 1 term. That's a common way to write that as well. You may prefer seeing it that way. What if they didn't start me at the very first term? Well, then maybe I'd say my a sub mth term gives me my a sub nth term if I have r to the m minus n term, so that I'm multiplying by that many changes in the terms. All right, given the arithmetic sequence as shown, find the common difference. Well, the easiest way to do that is take 2 side by sides and subtract them to check what that difference was. Here it was 4. Maybe I grab 5 and 9. 9 minus 5 gives me a common difference of 4. So here I definitely can see that the common difference is 4. Next they wanted us to find the 9th term. I do have the a sub first term, so I'll find a sub 9 is equal to my a sub first term plus 9 minus 1 common d. And this is going to look like the a sub 9th term equals -3 for our first term plus 8 times the common difference of 4, 32. 32 minus 3 sounds like 29. The a sub 9th term equals 29. Then they ask us to write a recursive rule. And that's the one where I want to say a sub n is equal to a sub n minus 1 using the previous term. So I subtract 1 from my n. And in this case, we have a common difference of 4, so I just need to hop to the next term, and that means just add 4 then. An explicit rule would say now I can jump right into a particular term value that maybe I want the 7th term there, a sub 7th term. Well, then what I would say is let's look at well, I'd have common differences. Maybe sometimes it's kind of handy to go to the term that's prior to this, like -7, and then add 4 times the common differences. 4 times d, which could be represented then if I'm want to go 1, 2, 3, 4, then it would just be the nth term of my sequence that I'm after. So if I want my a sub 7th term, in this case I could say a sub 7 is equal to -7 plus 4 times 7, and that would give me 28 plus a -7. It would appear that that should be 21. And indeed, I think if you keep counting up, you'll land there. Okay, one more bump maybe. No, that should get us 5, 6, 7. So really you're adding a 4 plus another 4 plus another 4. That would get us 12 plus 9. It would get us to 21. For the geometric sequence 1, -3, 9, -27, the common ratio, the same idea, we take two side-by-side terms and divide. So -3 divided by 1 says my common difference is a -3. Would it be the same if I chose these? -27 divided by 9 gives me common ratio of a -3. So my r, which is typically used to represent the ratio, is -3. The 10th term in ours would be a sub 10 is equal to the a sub first term, which we are lucky to have, and then it would be my r, which is -3, let's do it in general terms, r to the 10 minus 1. So I'm going to have my a sub 10th term being a sub first term, which is 1. My r value is -3 raised to the 9th power. Oh boy, I don't know what that is. And nor do I have it on my note sheet, you guys. Sorry about that. It's going to get kind of large. But that's what it would turn out to be. A recursive rule for the nth term. Sometimes these recursive rules, while we think they're kind of a pain, are actually the easier version to write. So it'd be a sub n equals the previous term, so a sub n minus 1, times our common r, or common ratio, which was -3. So that's all that would take. And then an explicit rule, I could say a sub n is equal to 1 in this case, which was our beginning value, and I'm going to multiply it by -3 times the n minus 1 term. Okay, because I started with the a sub first term there. All right. The last thing we have is an example here. They gave us the 2nd and the 5th term of the geometric sequence are known as -6 and 48 respectively. The first term, the common ratio, find, that's a keyword, find the first term, the common ratio, and the explicit rule. So, I know this video is getting a little long, so let's kind of get to it. I could think of the 5th term as being written as the a sub first term times r to the n minus 1. So I'd have 5 minus 1, which gets me to the 4th term. Likewise, the 2nd term would be the 2 minus 1 ratio. So this would be just a single 1 up there, right? So it'd be the initial term, a sub 1, times the number of ratios I need to get to whatever term I'm set at. And we could set up this nice little proportion and solve it. But the first thing I notice is a sub 1 can cancel with a sub 1. I have r to the 4th over r to the first equals negative 8. And I can subtract my exponents, right? Those rules still apply. So I get r to the third equals negative 8. And then I can cube root my r to the third, cube root, and it just so happens that we have a nice number here, right? R equals negative 2. So I've just figured out the common ratio between them. And that'll work there. I was going to try and show you another method that I could do, and just thinking through here. Would it work to say I have the a sub n? Okay, I just paused it for a moment to get this written down. We could say that the a sub nth term, what I wanted to finish with, is equal to a starter value that I happen to be given times a ratio raised to m minus n, the number of changes I need to have happen to get me to that term that I'm finishing with. So if I take that approach, I want to finish with the a sub fifth term. I know the a sub second term, and then that would be a 5 minus 2, or 3 changes, right, to get me up to an a sub fifth. I'm just drawing this out. 1 ratio, 2 ratios, 3 ratios to get up there. R times R times R will take me to that ending. Now, we know the a sub fifth term. This is just showing you an alternate method to do this work. And you could write your explicit equation like this. Divide by 6, we're looking at negative 8 equals r to the third. And of course, we come out with that same ratio of negative 2. And finally, they wanted an explicit representation of this sequence. So we could say the a sub nth term is going to be 3, which would be my starter one. How did I get that? Well, I knew my a sub second term was 6. I knew my common ratio was negative 3. So I took a sub 2, which is 6, and divided it by negative 3 to take me back down. Instead of multiplying up, I'm dividing to get down, and that would give me negative 2. Oh, hold it, I'm getting my numbers mixed up. R was negative 2, and it's going to take me then. R was negative 2. It finishes me at negative 3. Oof. Positive 3. A sub second was negative 6. You probably caught that. Negative. And there's the positive. So I get my a sub first term at 3. And then I would just say it is the r value, that's r there, to the n minus 1. Okay? Now, that's a nice intro. Hopefully I didn't bore you too much, but sometimes people just need to hear all that stuff again and see how those general formulas worked. There is the math lab that's open, and go ahead and complete your work on that. Have a great day, you guys. Bye-bye.